Hello everyone, my name is Hriday and today we'll discuss the topic diffusion through a stagnant gas film. Before we move on, I'll briefly introduce to the topic diffusion through a stagnant gas film. We'll consider a binary mixture of A and B where component A will be a volatile liquid A and component B will be a stagnant gas. So let's start with the very basic derivation which considers a steady state diffusion of component A through a stagnant gas B in a vertical tube. This is the figure for the question. We have a vertical tube and a volatile liquid A. Z is equal to Z1 is the interface of liquid A and the gas B. Initially, we will only have a gas stream of B, but as the time passes, the liquid A will evaporate into air, or we can say any stagnant gas considering B, and it will eventually be called gas stream of A and B. The mole fraction of A in the gas phase at Z is equal to Z1 is XA1 and XA2 at some Z is equal to Z2 at the end of the tube. We will assume the system operates at isothermally and constant pressure and the gases also behave ideally. What we have to do is perform a differential shell balance. We have a shell of thickness delta Z and will integrate it over the entire tube from Z is equal to Z1 to Z is equal to Z2. The question has been taken from BSL 18.6. So we'll start with the coordinate system. The coordinate system will consider Cartesian coordinate system because it is easier because it fits our geometry. We consider a differential element with shaded area. The shaded area shown is A, also this one too. We have a thickness, this is the thickness of delta Z. Flux entering at Z is equal to Z. This phase will consider at as Z is equal to Z. The flux entering through this phase will be Na computed at Z, this phase. Next we have rate of mass entering at Z is equal to Z. At this phase, rate will be the flux into the corresponding perpendicular area, which we have considered as A. Similarly, the rate of mass which exits this phase at Z plus delta Z is Na at Z plus delta Z into its area A. Will apply steady state balance over the element input minus output. There are no generation and consumption terms and will consider a steady state, so accumulation is also zero. Simplifying, we divide both sides by A delta Z and use the definition of derivative, which is we take delta limit delta Z tends to 0, which will give us this equation minus of dNA by dz equal to 0. For a binary mixture, we know Na will be Ja plus Xa into N. Ja will be molecular flux, which would be dAb dCa by dz, and N we can write for a binary mixture as Na plus Nb. For our case, we have Nb is equal to 0. So this equation will be simplified as only Na. Take Na into Xa into LHS and simplify the equation to form Na is equal to this corresponding RHS term. We take this equation and substitute here. So it will look like this. We get a differential equation. We just have to integrate it twice. So when we integrate it once, it will be just left as dxa by dz equal to C1. C, the product of C into DAB will be a constant and can be taken out of the differential, and it will be the product of C into DAB can be taken out of the differential and can move into RHS as 0. So we integrate it once and get the constant C1. Similarly, We integrate it again to get this equation. Now to get the constants C1 and C2, we'll use the boundary conditions, which is z is equal to z1, we have xa is equal to xa1, z is equal to z2, we have xa at xa2. Substituting and simplifying, we get these two constants c1 and c2, and when we substitute into this equation, we get xa as a function of z. So we have to compute the flux of A. So we'll get Na. We have to find Na. So to get Na at z is equal to z1 at the interface, we have to find out dxa by dz. We have the relation of xa as a function of z. So we can uh, take log and differentiate both sides. So we'll get dxa by dz. We substitute that and use the definition of xblm, which is the log mean of b, xb2 minus xb1 upon ln of xb2 upon xb1. We substitute and rearrange to get this final equation. So a simple problem based on this derivation, it will be 18.A1 BSL unsolved first question. Total pressure is given as 770 mmHg, slightly above ATM pressure. We have to find out the evaporation rate of CCl3NO2 into air. Air is a stagnant gas B here, and CCl3NO2 is the volatile component A. That air is a pure, we can assume that air is a pure substance. This will later be helpful in calculating XA2. Diffusivity is given, vapor pressure, and all the properties of the system are given. We'll start with XA1 at the interface of the liquid and the gas, which will be PA, the vapor pressure of A upon total pressure. We can find out the mole fraction, which is 0.0309. XA2 is 0 because it is assumed that air is a pure substance. Next we have XB1, which is 1 minus XA1 equal to 0.9691, and XB2 is 1 because XA2 is 0. So XB2 will be 1 minus XA2, which will be 1. Next we calculate XB log mean. For the formula we'll need XB log mean, so which is XB2 1 minus XB1, which is 0.9691, upon XBL upon the log of their ratios. So it will be 0.9894. We'll calculate the concentration of A, which will be P upon RT. Total pressure will be 770. Temperature is 298 Kelvin and R is 62363. The units of R will be in mmHg. The pressure units will be in mmHg. So to cancel out this, it will be all to maintain the unit consistency. The value of R is taken as this. So the Ca will be 4.14 into 10 power minus 5 mole per meter cube, and just substitute the formula to get the answer, which will be 1.03 into 10 power minus 8 mole per centimeter square second. Ca will be mole per centimeter cube. Rate is we know rate is equal to flux into area. Flux is Na, this one, and area is given as 2.29. Area surface area of liquid exposed for evaporation is 2.29 centimeter square. So area is this. We have a second in the denominator. To convert it into hour, we have to multiply by 3600. So this will be mole per hour. We have to find in grams per hour, so we'll multiply it by its molecular weight 164.35. So it will be this. This will be the final answer. Rate of evaporation is 0.014 grams per hour. Next up, we'll make it a little bit tricky. We have a question. The same methanol is evaporating into a stagnant air VB in a vertical tube of length Z2 minus Z1, which is 0.15 meter, and At the liquid surface, it is z equal to z1. xa1 is given as 0.12. At the top of the tube, z is equal to z2. xa2 is given as 0.01. The diffusivity is also given. So we'll start with equation of change approach. We'll start from the general species continuity equation, mass balance equation for component A in one dimension, and we'll simplify it. Then we'll use the derived expression to calculate the molar flux of methanol. Equation of change for isothermal mass transfer systems. We'll use the analogy of momentum transfer, like accumulation term. Accumulation term for momentum transfer is d rho by dt. In mass transfer, it will be same as d del Ca by del T. The convective transport term for momentum transfer, it is grad dot rho Vv. In mass transfer, it will be grad dot Ca into V. Similarly, for molecular transport, it will be this total molecular momentum flux, and the same will be here, grad dot Ja, the molecular flux for mass transfer systems. Ra will also consider Ra, rate of generation or consumption of species by reaction. Since there is no reaction, Ra will be 0 in our case. Ja will be grad dot Ja. If we simplify, it will be minus C dAb grad Xa. Grad Xa will be represented as del Xa by del X, del Xa by del Y, del Xa by del Z. Applying rate balance, because if we go into other coordinate systems, the area will change. So we always take a balance of rate, not flux. This will be the final expression. The Ra will be 0 because we do not have any reaction. We have molecular transport term, convective transport term, and the accumulation term. Accumulation is also 0 because we have steady state. Ra is 0. We consider only one direction, and for that, this will simplify into d by dz. Only we have the property change in one direction, that is z direction. So if we integrate this equation once, we get a constant C1, and we know Vz is equal to n by C. But since we have n is equal to Na plus Nb, but we have Nb is equal to 0, which is a stagnant gas B, Nb is equal to 0. So it will be simplified into Na upon C. Next, we substitute Na upon C here Vz to simplify this equation. We get Ca upon C as Xa, and the rest remains same. We know this. This is the basic definition of flux. Na is equal to molecular flux and convective flux. Ja is the molecular flux, and this is the convective flux. For B, component B, we can also write as this Jb plus Cb into Vz. And I've shown you earlier that Jb can also be written as this. This will be replaced by del xb upon del z because we only consider one directional. And for our case, nb is 0. So in this equation, we substitute nb is equal to 0. nb is equal to 0 and solve for Vz. We solve for Vz and we get Vz as this. We substitute into equation 1, this one. We substitute Vz into equation 1, we get this equation. We know xa plus xb is equal to 1. The mole fractions always add up to 1. So take a derivative of them with respect to z. This equation, we take a derivative with respect to z. It will be dxa upon dz plus dxb upon dz equal to 0. So we get this relation. We substitute this relation here. Yes, substitute this relation into this equation 2 to get the value of constant, which will be c upon 1 minus xa dAB into dXA by dZ. We cannot directly substitute this constant here to solve it. So we have to find something related to that. So we again substitute Vz into equation 3. This one. We substitute Vz here, and this is our major output, or we can say conclusion. C1 will be equal to Na. We'll substitute here and we'll get that the C1 will be equal to Na. This. So we replace in the original equation with C1 as Na. We rearrange, take Na to the left and rearrange to get the equation. Here xb2 and xb1, 1 minus xa is replaced with xb. 1 minus xa can be replaced as xb because xa plus xb is equal to 1. So 1 minus xa is equal to xb and integrate them. Finally, we use the definition of b log mean to replace this ln term. To replace this ln term, we use the b log mean, and this is our final expression, which is same with respect to shell balance. We'll solve a numerical with this, the part B of that question. Using the derived expression, calculate the molar flux of methanol. First, we'll calculate Ca, which is pressure upon RT. Pressure is given 1 atm, which is 101,325 pascals. Our standard units, SI units, and temperature is 298 Kelvin. So we get 41.77 mole per meter cube. XA1 and XA2 are given in the question. XA1 is 0.12, XA2 is 0.01. We can calculate XB1 and XB2, 1 minus XA1 and 1 minus XA2. Similarly, we can calculate XBLM, which is XB2 minus XB1 upon ln XB2 by XB1, which is 0.92. Finally, Na, substitute the values. We get Na as 5.33 into 10 power minus 4 mole per meter square second. So molar flux of ethanol will be this. Thank you. This will be all for today.